New York Times Connections is a game where you're given 16 words and tasked with finding 4 secret groups that share an attribute. These groups consist of definitions such as giant, huge, monster, and titanic, all meaning enormous, while harder categories consist of wordplay such as silly, mother, golden, and gray, all words where after adding goose to the end, each word becomes a common phrase. Some other clever categories are Latin words such as caveat, vox, quid, and ergo, and Mariah Carey #1 hits. These categories explore the hidden layers of words, their meanings, usages, origins, and cultural significance, and the process of finding these hidden categories displays the uniqueness of language, giving simple words infinite meanings. And here is an AI that can solve it. So here's the plan. There are 2 parts. 1, the AI has to figure out how similar each word is to each of the other 15 words. Then, in part 2, it has to choose groups of 4 that have the highest shared similarity level and then guess it. It then has to use the information the game gives back, whether that be incorrect, correct, or one away, to make a second guess. It then repeats, guessing until it gets all 4, or guesses the 1,820 possible answers. To determine word similarities, we'll use Word2Vec to create a neural network that predicts the most likely word to follow a given word. We'll train the model by splitting sentences into word pairs, where the goal is to predict the second word, given the first. This isn't our final objective, but it's a crucial step in the process. Since neural networks are based on math, we'll have to turn a word into a list of numbers. To do this, we'll use one-hot encoding, where we place a 0 for every position except the one we're trying to represent, where we put a 1. For example, to encode the word love, we'll set the position for love to 1 and all the other positions to 0. Next, we create a neural network that takes in this array of numbers that we gave it, and after traveling through a number of layers and being multiplied against values called weights, spit out another list of numbers. In our case, the return list will represent the percentage of certainty the AI thinks the following word is. Currently, it is random as our weights are random, but after a process called backpropagation, where the weights are changed based on how wrong its output is, we can achieve a pretty good output array. Small values are given to those corresponding to I and love, and a high value is given to LeBron, which is the correct output. Training also has to be done on the other pairs, but eventually we can have a neural network that can predict the next word in this sentence. This example only uses one sentence to train. If we use an extremely large dataset, say Wikipedia, it will create a model that can predict which words are most likely to occur after another one. This strategy is also the basis of many large language models, such as ChatGPT. But wait, we aren't trying to predict a word, we are trying to find the similarity of 2 words. To do this, we won't be using the neural network, but we will be using the weights that have been trained for the neural network. By comparing the weights of words, we can find that similar words have similar weights. The reason this is because if we get a large enough corpus of text, similar words are more likely to have similar context words. For our example, let's say we train it with another sentence, I adore LeBron, which is a sentence you'll find across the internet. Once we train a model that can successfully return LeBron to both of the words love and adore, and turn their weights, which are just a list of numbers, into vectors in space. Keep in mind that this demonstration is simplified to 3 dimensions. The actual model will use more than 200. Then, if we cosine the angle between the vectors, or find the cosine similarity between them, we get a number between -1 and 1 that tells us how similar they are. By comparing this to another word, say LeBron, we can see that the similarity is much greater. In our actual model, the similarity given between love and adore is 0.69, while that of love and LeBron is merely 0.26, a massive difference. That is the beauty of Word2Vec. The AI has no clue why words are similar, just that they show up with similar contexts more likely than not. Back to our first example of connections categories, the AI can easily figure out that Latin words are closer to each other because they are more likely to show up beside other Latin words, while Mariah Carey songs are more likely to show up beside the words song, hit, and of course Mariah Carey. Now that we can find how similar 2 words are to each other, the AI has to choose the best possible group of 4. First, we have to calculate the similarity of every word to every other word. In this visual, the nodes represent words and the lines represent the cosine similarity between the words. Finding communities in graphs like these is called clustering, and in actual useful computer science, graphs such as telephone numbers consisting of millions of values require fancy algorithms to cluster. However, there are 2 things that make our job a lot easier. For one, we know that each group must have a size of 4. Secondly, the size of the pool of nodes we can choose from will always be relatively small, either 16, 12, 8, or 4. This lets us brute force every single possible group of 4, and using some sort of ranking system, find which group of 4 has the highest likelihood of being a category. Calculating every single possible group may seem inefficient, but in such a small pool, it would have to calculate 16 choose 4 possibilities in the worst case, which is 1,820, which to a computer is almost negligible. Next, the ranking system. To find how well a group is compared to other groups, I have used two values called density and conductance. Density is the average cosine similarity inside the group, while conductance is the average cosine similarity between members of the group and outsiders. By normalizing both numbers into a decimal between 0 and 1, and then by flipping the conductance, we can add both numbers together to achieve a pretty crude measurement of how good a group is. Then, by applying this method to all 1,820 possible groups, the algorithm now knows which groups are the most likely to be correct. The next step is to code the logic of the program. For this, I'm going to represent this in a decision tree. In summary, the algorithm first calculates its initial guess from the method described earlier. If it is correct, then hooray, we remove the words we picked from the pool and restart the tree, this time calculating the best possible guesses from a smaller pool. If it is incorrect, that sucks, we'll just guess the next most likely. However, if it is one away, the AI will search for what I've called the weakest link, finding which word of the force removal will have the greatest density and conductance in the remaining group. Then it will find a replacement word that gives the highest density and conductance, and then it will guess that guess. And if the game responds with correct, then yay. But if the game responds with one away, it means that our weakest link was correct, but our replacement value was not, so we find the next best replacement. If the game responds with incorrect, however, we have to find a new weakest link, and start the process over again. This repeats until we find all correct answers. Next, we have to code the game itself. I found a website that contained every single past connections game and answer and copy-pasted it and parsed it into an answer sheet for the game. Then, by using Pygame, I was able to make this interface that lets you or the AI play. On the right, the top guesses are ranked with their corresponding density plus conductance. I can guess the best group by putting a 1, which if I let the AI play, it will always choose, and the game will display whether it is correct, incorrect, or one away. Then it recalculates and I guess again, and the correct answers are removed from the pool. Next, by running the AI in almost 400 games, I was able to create this graph. This histogram depicts the number of mistakes the AI made and how often. The average amount of mistakes was around 10, which was way better than a random program would have performed, but leaves a lot of room for improvement. One way I thought of improving the algorithm laid in the density and conductance I mentioned earlier. In the current state, it just mashes the density and conductance together like a caveman, but by adding coefficients to each of these values and using a genetic algorithm to optimize these coefficients, we can create a measure of goodness of the graph that is more suitable for connections. So let's start, but while past me codes up the genetic algorithm, let me first explain what the hell that is. In normal machine learning, in which Word2Vec uses, layers, weights, and backpropagation are used. Genetic algorithms throw that out the window and instead mimic evolution. By first getting a random population of algorithms, in my case just the coefficients beside the two values, it will get the best performing algorithms and kill the rest. In our case, the best performing algorithms will be the ones whose coefficients get the lowest average amount of guesses. Then, we perform small changes on the surviving algorithm, creating another population. I ran this overnight with over 100 generations, eventually achieving these two numbers. I think it's quite interesting how the density is obviously favored, yet the conductance is not thrown away altogether either. But now let's plug them into the AI and see the graph. Here's the final graph. The average value decreased by around 10% to 9, and the mode guesses decreased to 3. In normal connections, you are given 4 lives, and the AI wins around 30% of the time. Although most experienced connections players would still probably beat the spot, I think it's pretty incredible how a game that relies so heavily on human intuition can be solved to such a degree. Looking at some of the examples the AI completely failed on, they are quite understandable and sometimes quite funny. One of them was this one, Connections 336 on May 12th. The double category of acronyms and category cocktails minus place names completely threw it off, and it solved it in a terrible 42 guesses. But seriously, what kind of category is this? Another type of category that the bot sucks at is categories like words that include 3 Gs, like in these connections. The bot completely fumbled in this one, solving it with an incredible 40 mistakes. However, there are quite a lot of connections games like this one, where it knows immediately that envy, greed, lust, and pride belong together, then that loris, sloth, snail, and turtle are together. What the hell is a loris? I don't know, and the bot doesn't know either, but it knows that it appears next to words like sloth and snail. Then it gets flock, pack, pod, and school, and gets the last one automatically. All in all, the AI's ability to find these hidden attributes is pretty impressive, but it falters at categories that describes a spelling, or have nothing to do with its meaning. But despite these setbacks and wasting half a summer I should have used to study, I still have quite a lot of fun on this project. It taught me valuable techniques in the field of AI, but also its limitations, that some activities are just more fun to be done by humans.